Okay, so we're going to start chapter 6 in this video with 6.1, and we'll probably get into section 6.2 as well. 6.1, though, is just the introduction of the new type of function we're going to be dealing with, which is a function of multiple variables. So multiple variables meaning multiple input variables. All right, so let's start with an example from, I guess, geometry. So this example is, you don't need to know this function. It's just an example to illustrate a simple place where something like this might come up. So the volume of a cylinder is, so let me draw a picture as I write this. Okay, so I have a three-dimensional object here, a cylinder. It's a circle at the top and the bottom, and then it's just extended through space here. Okay, so the volume of this thing is V equals, we have two numbers we need to use to compute this. One is the radius, so the radius of the circle at the bases of this cylinder, and the other is the height. Okay, so based on these two numbers, the formula for the volume is pi, number pi, which we haven't used very much in this class, but the pi number 3.14 or whatever, pi r squared times h. Again, don't worry about where this comes from. I don't care about that. The point is, this can be thought of as a function, but there are two inputs I need to know. I mean, pi is a constant. It's not a variable, but r could be any positive number, h could be any positive number. So this is really a function, and the notation for it, when there are multiple input variables, like again, r and h, they're both input variables. They don't depend on each other. I can pick any number for h, and I can pick any number for r. Those are two separate choices. But once I choose those two numbers, that will determine v. That'll determine the volume. So v is the dependent variable. R and h are both independent variables. So the notation for a function with more than one independent variable is, we have parentheses, v of, but we have parentheses, and then we separate the different independent variables with commas. So this is my formula and function notation here. So then, just for example, if how do I do this? Let me make some space here. So just to illustrate the usage of this, if we say r is equal to 3 centimeters and h is equal to 7 centimeters, then in function notation, r is the first independent variable in our parentheses, so we put a 3 there, and h is the second independent variable, so we put a 7 there. So I'm evaluating this function at a given pair of inputs. So I'm just replacing each r with 3 and replacing each h with a 7. So what is that? That's 3 squared is 9 times 7 is 63. So this is 63 pi, which is approximately, I don't know, 197.92. And this would be, what would the units on volume be if my measurements were in centimeters? Then the volume would be a three-dimensional unit, so that'd be centimeters cubed. So centimeters squared times another centimeters gives me centimeters cubed. So that would be the volume of a cylinder whose radius is 3 centimeters and whose height is 7 centimeters. Okay. So it's a function of two variables. We could also have functions of more than two variables. Let's for now look at a few examples with two variables. So our kind of just like with single variable functions, our default variables were x is the input, y is the output. For two variable functions, meaning there are two inputs, my default variables are x and y. So f of x, y means we have a function with inputs x and y, and then our default output variable is then z. So just like y equals f of x is our default setup for single variable functions, z equals f of x, y is our default notation for a two variable function. So just for practice, all right. So suppose we have the function f of x, y equals 3x squared minus 2xy minus y squared. So I get some formula that involves x's and y's. Then calculating stuff, our easy kind of problem is just given an input pair. So 5, 0, for example, this is just a calculation problem. Every x in my formula gets replaced with a 5. Every y in my formula gets replaced with a 0. So this becomes, go on, make up your mind, 3 times 5 squared minus 2 times 5 times 0 minus 0 squared. This is all 0, so we get 5 squared is 25 times 3 is 75. I won't belabor the point here. Let's just do one more. F of excuse me, f of 2 negative 4. We plug these things in. 3 times 2 squared minus 2 times negative 4 minus negative 4 squared. So that's what? 3 times 4 is 12. Minus a minus makes a plus. That'll be 4 times 4 is 16. And then minus negative 4 squared is 16. So that's minus 16. So that gives me 12. All right, so again, my two variables, x and y, they're independent of each other. Whatever I choose for x and whatever I choose for y, those are separate things. So if we want to talk about, we're not going to worry about graphing these too much, but I do want to mention it. If you want to talk about the graph of a two variable function, so z equals f of x, y, the domain for that, there might be restrictions, but the domain is, it's a collection of x values and y values. So the domain for this lives inside the xy plane. So let me draw it here. The way I want to think of it is the x and the y axis are, this is going to be a three-dimensional drawing now. The x and the y axis are like the floor. The xy axis is like the floor here. The output axis, the z axis, is going to be introducing a height variable. So these all extend in every direction. So I get a three-dimensional picture here. You have to imagine one of the axes coming out of the board at us. So that's, in this case, the x-axis, we're envisioning it as pointing out of the board. So then the domain is like the floor here. It's the xy plane sitting at height 0. The graph of this function is going to be some, let me use a different color. The graph is going to be some surface that's lying above or below the xy plane. so these are hard to draw. So something like this maybe. Yeah, I don't know. I don't know if that helps or not. But the point is, if I pick an X and a Y here, so maybe this is 5, 3 or something. I come out to 5 on the X axis and out to 3 on the Y axis. Then 5, 3 is in the XY plane. Then I plug that X and Y pair into my function, and it'll spit out a Z coordinate that'll tell me the height of my surface above that point. So this distance here would be the Z coordinate. Okay, so this is just to give you a sense of what the graphs would look like. We're not going to get into the graphing of two variable functions. If you have more than 2 input variables, it's like 3 input variables, then I can't even draw a picture of the graph because it would be a 4-dimensional picture, which we can't visualize, really. We certainly can't draw it. Okay, so I just wanted to have this in the background of what these graphs look like, because as we introduce some concepts, we may want to think about these, but again, we're not going to be drawing them as part of our problems. We're not going to be drawing 3-dimensional pictures. Yeah, so we can also have, say, just to do one example, we could also have three variable functions. In that case, our 3 variables are generally X, Y, and Z. The output variable, I would have to pick a new letter, maybe W or something. But the function f of x, y, z would then be an expression that can involve these 3 variables. So maybe it's z times 3 to the x power times 2 to the y power. Then if I want to evaluate some input output pairs, so I pick a value for each of my 3 inputs. That gives me enough information to calculate the output. So z is equal to 5, x is equal to 1, so I have 3 to the 1 power, y is equal to 2, so I have 2 to the 2 power. So 5 times 3 times 4, that's 12 times 5 is 60, and so on. So again, we'll do 2 examples just to have something here. 0, -1, 8. So I have 8 times 3 to the 0 power times 2 to the -1. 3 to the 0 is 1. 2 to the -1 is a half. So this is 8 times 1/2, which is 4. All right, so this is just the introduction of what kind of functions we're dealing with. So they're just formulas that involve more than one variable. Let's talk about the calculus of it. So this is now where we start section 6.2. We don't want to get into, so again, to remind you what the major topics of calculus were. At the very beginning of the semester, I said calculus basically has 3 major concepts. We have limits of functions, we have derivatives of functions, which are rates of change, and we have integrals of functions, which are about accumulating values of a function over a domain. for our purposes, we're not going to worry about limits of two variable functions or multiple variable functions. We won't have time to get to integration of two variable functions, but we will spend time talking about derivatives in a multiple variable situation. So these are called partial derivatives. Okay, so let me introduce these with a two variable function. These can easily be extended to multiple variable functions with more than two variables. Okay, so the notation, before we worry about what they are, let's just talk about the notation and how to pronounce it. Okay, so if I have two input variables, I can take a derivative with respect to one of them at a time. So I can say, I can't use f prime as my notation because there's two variables, so which one would prime refer to? So instead, I use a subscript with the variable I want to take the derivative with respect to. So f sub x, this means the partial derivative with respect to x. Or another way to write it, so if you think back to the derivatives in a single variable function, we had f prime was one notation. This is the analogous notation to that. The other one was the dy dx notation. For this partial derivative situation, it would be like dz dx, but for reasons that I don't really know, d is not fancy enough for a partial derivative, so we use this fancier d, which is sometimes pronounced del, but this thing, z, so I'll pronounce it dz over dx. It's just, when you see it typed, it won't be the ordinary d, it'll be this funny cursive looking d or script looking d. So dz over dx means the partial derivative of the output variable z with respect to x. Okay, we have the same things for y. So similarly, f sub y means the derivative of f, the partial derivative of f with respect to y. That's the same thing as dz dy. Okay, so let's first let me try to explain what this is, what it means, and then we'll do lots of practice computing these things, because that's the main thing, is how to compute these things. Okay, so let's just talk about one at a time here, because I mean, it's the same concept just with a different variable. F sub x is the rate of change or slope of the function f of xy if y is held constant and x is allowed to vary. Okay, so let me try to, here's where I really like to be in a classroom and be able to do stuff in 3 dimensions. Let me try to draw some sketch of a surface here. All right, so my drawing skills are not great, but we've got some graph. Again, this is sitting above the XY plane. Let me not draw the z-axis because I think that'll just make it too muddled here. So let's imagine we're standing on this surface someplace. So above some XY point, we go up to our surface, and we're standing on the surface there. Okay. If y is held constant, then I'm not moving in the x direction. Sorry. Say that again. If y is held constant, I'm not moving in the y direction. I'm only allowed to move in the x direction. So as I come out of the board in the x direction, I have a curve along this plane. Or sorry, a curve along this surface. So this red stuff here, that's coming out of the board at us, but its height is changing as it comes out of the board. So it's coming out of the board like this. At this point, I can think about what's the slope of that curve at that point as I come out of the board. So how fast is my height changing as I move out of the board? That's what f sub x is at this specific point. So f sub x will be a function still of xy. So I'm looking at this exact xy pair, this point here. I go up here. F sub x at that xy point is the rate of change of my height as the person walking on this curve walks in the x direction, in the positive x direction. Okay. Similarly, f sub y would be the rate of change if, let me erase, f sub y would be the rate of change in my function if x is held constant. F sub y is the rate of change or slope of f of xy if x is held constant and y is allowed to vary. So let me alter my picture now. This is maybe easier to see. So I add a specific xy pair that gives me a point on the curve on the surface here. And now I'm not changing x, so I'm walking sideways along this surface. I'm going in the positive y direction. That gives me a curve along the surface. That curve will have a slope at that point. That slope is f sub y at this point. Okay, so these are both rates of change. Both of these partial derivatives are rates of change in the function, but only as I'm allowed to change one of the input variables at a time. I keep one variable constant and change the other variable. It'll tell me what is the steepness of my surface if I'm walking in that direction. Okay, so let's look at some examples. So let's do an easy one first. F of xy, let's say it's x squared plus y to the 5th power. I want to compute my partial derivatives, f sub x and f sub y. Okay, when my subscript is x, that means I'm thinking of x as a variable and I'm thinking of y as a constant. So I'm taking the derivative of the function with respect to x. That means in my formula, wherever I see a y, I treat it as if it's just a number. So if this was like x squared plus 2, and I took the derivative of that, the 2 would just disappear because the derivative of a constant is 0. So my derivative with respect to x would be 2x plus 0, just for emphasis. Because y to the 5th, that's constant with respect to x. It's not changing. If I change x, the y to the 5th is not changing at all. So f sub x of this function is 2x. F sub y, I'm taking the derivative with respect to y. Now I treat x as if it was just a fixed number, a constant. So the derivative of x squared would be 0. The derivative of y to the fifth would be 5y to the fourth. So 5y to the fourth would be my partial derivative with respect to y. Okay, this was a very simple example. Let's do one that's a little bit trickier. Let's mix up our variable names here. So g of xy is a x cubed y to the fourth plus 8y. That's an 8. So g sub x of xy. So it looks like a product. I mean, it is a product. But as far as x is concerned, if we're doing derivative with respect to x, the y part is just a number. So you should think of this function here, x cubed times y to the fourth. You should think of that as being similar to something like 4x cubed. So instead of 4, we got y to the fourth. So when I take the derivative, that constant part, it just stays there. I'm taking the derivative of the x part and keeping the existing constants that are already there. So I would get 3x squared y to the fourth. And then the plus 8y, that doesn't have any x's. There's no x's in that part, so its derivative will just be 0. So 3x squared y to the fourth. G sub y, well, now the x part is constant, is basically a coefficient. Taking the derivative of y to the fourth would give me a 4 that comes down. The x cubed is already there, and I'd have y cubed left over for my power rule. But now the 8y, it involves y, so its derivative is now 8. So 4x cubed y cubed plus 8 is my derivative with respect to y. Okay, so let's do another. So the best way to learn these is just to do lots of different types of examples. So here's another one that's a little bit trickier. F of xy equals, let's say, y times e to the power x squared y. I want my two partial derivatives. Okay, so you have, when you do these, you identify what is the variable that I'm differentiating with respect to, in this case x. Every other variable is a constant. So you look at that and think, what kind of function is it? It's like it's a number times e to a power of x with another number up there. So this is basically just an exponential function e to a power involving x. So the derivative would be a chain rule problem. We keep the coefficient that's already there, y. The derivative of e to a power is just e to that power. So I'd have e to the x squared y, but then I have to multiply by the inside derivative by the chain rule. So that would be, with respect to x, the inside derivative would be 2x times another y. So that's the derivative of the upstairs stuff. So now simplifying that, that's, I've got 2x, y times y is y squared, e to the x squared y. compare that to f sub y for this function. So now you look at this function, y times e to a power involving y. That's now a product of two things that both involve y. So for the y derivative, I have to use the product rule here. Make a note of that. I didn't use the product rule for x because the two functions involved, only one of them involved x. One of them only involved y in the product. So with respect to x, that's not really a separate function. That's just a coefficient. But with respect to y, both parts involve a y. So use the product rule. The derivative of y would be 1. Leave the second function alone. Plus, now we leave y alone and do the derivative of the e part. So again, that's a chain rule. E to the power times the inside derivative with respect to y. Well, it's just a number times y. X squared times y. That's just a number times y as far as y is concerned. So its derivative would be the number, x squared. So I don't really have to rewrite this, but I could write it like this. All right. Yeah. All right, let's do another one with a different notation. Okay, so let's do one without function notation just to see what that looks like. Suppose we have z equals ln of y cubed plus x. Then my partial derivatives look like this. dz over dx with our fancy d. So if you look at this, with respect to x, this is a logarithmic function because x appears inside the logarithm. So the way I take the derivative is with a chain rule. The outside function is ln. So derivative of ln is you take the inside stuff and stick it in the denominator. And then I have to multiply by the derivative of the inside with respect to x. The inside derivative with respect to x, y cubed is a constant, so it disappears. The derivative of x is 1. So I just put a 1 on top. dz dy is very similar. It's the same type of function. It's a logarithm with the variable on the inside, so a y on the inside. The outside function's ln again, so the derivative of the outside function is you take the inside and stick it in the bottom. But now we have to multiply by the inside derivative with respect to y. The derivative with respect to y of the inside will be 3y squared. So 3y squared divided by y cubed plus x. Okay, let's do one more. Let's do a 3-variable function. F of x, y, z equals x squared y plus x times e to the 4z. All right, so now I have three variables, x, y, and z. So there are three different partial derivatives. One for x, one for y, and one for z. So let's do each of them. F sub x. I take the derivative with respect to x. That means I treat all other variables as constants. So the derivative of x squared y with respect to x is going to be 2x. Y is just a constant multiplier, so we leave it there, 2xy. Plus x e to the 4z. E to the 4z by itself doesn't involve any x's. So as far as x is concerned, e to the 4z is just a constant multiplier. So I have basically a number times x. The derivative would be the coefficient, the number. So plus e to the 4z. F sub y would be, now we treat x and z as constants. So in particular, if there's a term that does not involve y at all, like x e to the 4z, there's no y there, that's just a constant, so its derivative is 0. So the only place y appears is right here, x squared y, and x squared is like a number. So a number times y, its derivative would be the number, which in this case would be x squared. Right? Finally, f sub z, that's the derivative with respect to z. Again, we only care about the terms that involve z. X squared y has no z's, so its derivative would be 0. Then this part, x e to the 4z, that's basically just an exponential function for z. X is a constant, so we keep it. The derivative of e to the 4z would be e to the 4z times 4. So that's 4x e to the 4z. Right. All right, so I think the way I'll do it is, we're not quite done with 6.2. We want to talk about second partial derivatives, or second order partial derivatives. That's where we take the derivative more than once. So we need to talk about that. I'm going to wait for until the next video to do that, because we also will talk about section 6.3, which is using partial derivatives to find local maximums and minimums of a two variable function. And for that application, it's going to use those second order partial derivatives. So putting those two topics together will make sense. I think I can do it all in one decent length video. Yeah, so from this video, you have enough information to get started on homework 14. Homework 14 covers 6.1 and 6.2. We've covered 6.1, and we've covered about half of 6.2, I think. The rest of it will be in the next video. And at that point, I will also tell you which problems to worry about on homework 15. All right, so I'll stop the video here.